In this series of Continuum Mechanics lectures, in this video we are going to talk about time rates of change and surface traction. Suppose phi is some quantity which varies throughout a body in space and time. We can regard phi as a function of t and either of material coordinates or spatial coordinates. In considering rate of change of phi, we want to know how phi varies with time following a given a particle. So the rate of change of phi following the particle having material coordinates as xr is given as dou phi by dou t. Phi is a function of xr comma t, which gives the rate of change of phi with material coordinates held, components held constant. If you consider in terms of spatial coordinates, it's the rate of change of phi with spatial coordinate held constant. So both of these rate of change of quantities is a different, both of them are different. So we want to find out the conventional notations uh, for the material derivative. So we give a notation as capital D phi by capital dt. So d phi by dt with d as the capital. This denotes the material derivative, that is partial derivative of the phi with respect to t. Phi is expressed in terms of material coordinates. These material coordinates can also be expressed through spatial coordinates. So once you express the material coordinates in the spatial coordinates, the derivative can be expanded as two terms. One has the partial derivative with respect to time, the other we have partial derivative with respect to spatial coordinates, and the velocity of the velocity with respect to spatial coordinates. So this defines the material derivative of phi. So one can also find out the change in the phi with from the spatial coordinates changing from xi to xi plus vi delta t and t to t plus delta t, and find out the change that gives you delta phi, and when the delta t tends to 0 you'll get the material derivative. It's exactly equation 14 you get. So now let's find out the material derivative of the velocity, what expression you get for velocity. So we find the acceleration of a particle is defined as rate of change of velocity, that's the material derivative of the velocity. So we have the two terms, one with respect derivative with respect to t, and the velocity of the spatial coordinates, and the velocity with respect to derivative of the velocity with respect to spatial coordinates. So this defines the acceleration of the particle. So one can get this expression by taking the velocity at the two spatial coordinates positions and taking the difference and divided by delta t, and when delta t tends to 0 you'll get the same expression as given in equation 16. So this is one example. We'll see another example. Let's take the velocity expressions as v1, v2, v3 given in equation 18, where we have only component along v1 and it is expressed in terms of spatial coordinates. Now the material derivative is given by taking the derivative with respect to spatial coordinates and the velocity component, and with respect, and also plus derivative with respect to time. So you will get the material derivative of the velocity, and one can express that in terms of spatial coordinates as well as material coordinates. So what is surface traction? Suppose a part of the body occupies a region R which has a surface S. So let's take a point P on the surface, n be the unit vector directed outward normal to the surface at the point P. Delta S is the small area element which contains the point P. So it is assumed that normal to the surface is uniquely defined at the point P. So let's assume that there exists a force on this material surface element, and that force is given by delta p equal to T n delta s. So the the force per unit area is given by Tn. So this force is called as surface force, and Tn is called as mean surface traction. It is nothing but the force per unit area. When delta is taken to the other side, it will be delta p by delta s. It's the force per unit area. So that gives the mean surface traction. So the Tn will only, it depends on the position p and the direction of the unit vector n. And the Tn is defined as delta p by delta s, and delta s tends to 0. It gives the surface traction. This mean surface traction becomes surface traction when the surface tends to delta s, surface element tends to 0. And it is defined through the unit normal outward to the point P. So at each point P there exists a vector Tn associated with each direction through point P. So let T1, T2, T3 be the traction vectors associated with direction E1, E2, E3. So now that this T1, T2, T3 is expanded in the terms of E1, E2, E3, and each direction has a corresponding vector. So E1 vector has a T1 traction vector. So this T1 corresponding to the E1 vector. So it has the three components along three directions. So we'll get a tensor when you expand T1, T2, T3 in terms of basis E1 dyadic E1, EI dyadic EJ. When you expand that, you will get a tensor component. These tensor component, so the quantity which we Tij is called as stress components. Thank you.